Good morning, everyone. Good evening, everyone. Uh, I'm Rain Jisma. Good evening, everyone. I'm Rain Jisma. I'm the TA for the course Fabrication Techniques for MEMS-based sensors from the clinical perspective. So, this week we'll be having the live session on week 5 content. So, whatever content that was covered in week 5. So, let's start. Before we start, I would like to just uh, about. So this is about me, and every week from Monday from 6 to 8, we'll be having the live session. And in case you have any questions, you can reach me at rayanrjisma@gmail.com. So first, we'll start with a quick recap of the various content that was covered in the week 5 session. So first, we see. So we had some content regarding the microfabricated devices for biomedical applications. So in this, we saw different kinds of MEMS devices, like micro heaters, diaphragms, and IDE. So IDE is interdigitated electrode. So the device that is used for the biomedical application contained a combination of these three. So here we also saw how to fabricate them and what are their applications. So another topic that we saw was cancer diagnostic tool. So in cancer diagnostic tool, we saw how MEMS is used for the cancer diagnosis and especially for the breast cancer. So we also saw what is the anatomy of a breast. So uh, the breast generally comprises of three types of tissues. So one is duct, lobe, and fat. So this is supported by the pectoral muscle. The breast is supported by the pectoral muscles. So depending on in which region we have the cancer, we have different types of cancers. So like ductal cancer, lobular cancer, or if it is have the cancer is present in multiple regions, then it is called as multi-tumor breast cancer. And if the cancer is inflammatory, then it is inflammatory breast cancer. If it is having some mucus secretion, then it is mucinous breast cancer. So there was also a discussion regarding two types of cancer cells. One of them was invasive, where the cancer cell will spread to other parts of the body, and the other was non-invasive. So in this case, the cancer will not spread to other parts of the body. Then in diagnosis, we saw that instead of using biomarkers in order to determine whether a person is having cancer or not, we could use certain properties of the tissue, which is the cancerous tissue, which is different from that of the other normal tissue. So some of these properties were mechanical, electrical, and thermal. Then we also saw the process flow for the fabrication of a micro heater on a glass substrate. Okay. So these were the contents that were covered in week 5. So next we can move on to the problem solving session. So, first problem is uh, glass wafer to silicon bonding can be done by A. Plasma bonding, B. Direct wafer bonding, C. By using adhesive, D. Anodic bonding. So, what do you think the answer is? Okay, so first let us start with problem one. Glass wafer to silicon bonding can be done using A. Plasma bonding, B. Direct wafer bonding, C. By using adhesive, D. Anodic bonding. Okay, so what is bonding process generally? So bonding is a process by which we are making two surfaces which are generally flat and clean. We are making them like stick with each other, like so that by applying some suitable amount of force, we will not be able to like break them apart. Okay, so uh, which of the following bonding can be used for glass wafer or silicon bonding? Okay. Uh, so now let us see what does each of this bonding mean. So in plasma bonding, so the name suggests that we are using plasma for bonding, right? And where do we use this kind of bonding technique? We use this when we don't want high temperatures. And also in the case where we are having some materials which will have different thermal expansion coefficient. So let's say I'm having two wafers which I want to bond together. If those two materials will expand differently under temperature, then what will happen is that like after bonding, let's say when I go back to room temperature, they will get contracted at, at different rates. So the bonding will come off. So in those cases, we can use plasma bonding. So in plasma bonding, what we'll do is we'll use plasma to modify the surface so that when we bring two wafers together after their surface is modified, and when we apply suitable amount of pressure, they will get bonded together. So let me say one example. If I'm having a PDMS wafer, and I want to bonded it with another PDMS wafer. So PDMS is a polymer material. So we cannot do the bonding at very high temperature. It cannot be processed at very high temperature. So what we can do is that first we can take one PDMS wafer and we can expose it to O2 plasma. So this O2 plasma will create some sort of SiOH bonds, like SiOH dangling bonds on the surface of the PDMS wafer. Then when I expose my second PDMS wafer to O2 plasma, again on the surface I'll have some SiOH bonds. So when I bring these two PDMS wafers together at higher pressure, then what will happen is at the interface there will be some SiOSi bonds formed. So these bonds are very strong, and with the application of suitable amount of pressure, we can bond the two PDMS wafers. So instead of two PDMS wafer, we can also bond a PDMS wafer with a glass substrate using the same plasma technique. Okay. In direct wafer bonding, what we'll do is we'll just bond the wafers without any intermediate layer between them. Like we will not use any adhesive or any metal to bond between them. So in direct wafer bonding, uh, it is just based on the chemical bonds between the two surfaces of the wafer. So generally, And most commonly, this direct wafer bonding is also called as fusion bonding. It is used to bond two silicon wafers together. So when we bring these two silicon wafers in contact with each other, then there'll be some van der Waals forces between the two silicon wafers. So when like we are applying high temperature, the bond like strength will increase. So this is some sort of a permanent bond. So at higher temperature, some sort of covalent bonds will be formed between the two wafers. In the third option, it is mentioned that we are using adhesive for bonding. So in this, like generally what we'll do is, we'll have two wafers. We'll have some sort of adhesive material. So this adhesive material can be either some sort of polymer, or it can be spin-on glass or photoresist. Then we'll have another wafer. So we'll apply suitable pressure and low temperature in order to bring about this bonding. So this type of bonding can be used like to bond the surfaces which are non-planar as well. Non-planar means, like say if there is some sort of roughness in your surface, if we are going by direct wafer bonding, then what will happen is like the regions where it is not planar will not get bonded together. So there will be some formation of void. And at those places, if the void formation is sufficiently large enough, then the bonding will come off, means the two wafers will come apart. Then the last option is anodic bonding. So what happens in anodic bonding is that we'll have a silicon wafer and a glass wafer. So anodic bonding is a bonding where we will do the glass wafer to silicon bonding. In anodic bonding, what we'll do is we'll have the silicon wafer which is placed on, near the which is connected to the anode. And we'll have the glass wafer. This is connected to the cathode. The entire setup will be kept on a hot plate. And we'll be applying some amount of pressure or any force, so that the both the wafers are in contact with each other. So what happens is that when we are applying some amount of electric field across this configuration, there will be some sort of depletion layer that is formed in the glass. So another important thing is that this glass will have some sort of cations present in it. So what will happen is, near the interface of the glass and the silicon, there will be some O2 minus ions that are formed due to the electric field. And in near the silicon, there will be some positive ions formed. So what happens is that when we are supplying high temperature by using the hot plate, and we are also giving a large amount of force so that proper contact is made, then the O2 minus ions will form some bond with silicon ions. And what kind of bond forms is OSIO. So this bond is also called as siloxane bond. It is a very strong bond. And this kind of bond is like this type of bonding becomes permanent bonding. So the answer for problem 1 is glass wafer to silicon bonding can be done by anodic bonding. So that is the correct answer. And so here you can see some of the various wafer bonding techniques where we do not use any intermediate layer. That one is fusion bonding, where we bond between two silicon and silicon wafers. In anodic bonding, we'll bond between glass and silicon. Then if you are using some sort of intermediate layer between two wafers, then depending on the type of the intermediate layer, whether it is a metal or non-metal, there are different types. If it is metallic, then there is a thermocompression bonding. So where we are applying high temperature along with large compressive force. In eutectic bonding, like we apply large amount of temperature, and we use certain materials which have this eutectic melting point, in order to bring about the bonding process. In non-metallic bonding, there are two types of intermediate layers that we can use. One is glass frit, which is some sort of porous glass, and it has a low melting point. And the other is adhesive, where like the adhesive can be different materials, like some kind of polymers, or it can be photoresistance more. So this is that's the answer for the problem one is anodic bonding. Uh, is this clear? And I hope that this will be an interactive session. Uh, so one thing I wanted to confirm is the screen visible? Are you able to see the slides and whatever is being marked on the screen? Hello? Okay, so now let us move on to the next question. Problem 2. Which of the following is the process that is preferred to clean a new wafer after procurement? A is RCA cleaning, B piranha cleaning, C solvent cleaning, D blow dry. So what do you think is the correct answer? So what do you think like is the correct answer for this question? Any suggestions? So here one important thing to note in this question is that it is asked like what is the process that is preferred to clean a new wafer, right? After procurement. So first, before we like see what is a cleaning process and what are the options indicating, there are three main contaminants in in a wafer that we generally want to avoid. One is organic contaminants, inorganic contaminants, and the third one is ionic metallic or ionic contaminants. So like we want to avoid all these kind of contamination, but in general this ionic contaminants are very like they are the most highly we want to avoid this kind of contaminants. Then the second most worst contaminant is organic contaminant. So this organic contaminant can come from human person, like from fingerprints. If our fingerprints are on the wafer, then we'll have organic contaminants. And also various organic particles can bring these contaminants. So in order to remove these types of contaminants, we have various cleaning processes. So one of them is RCA cleaning, piranha cleaning, solvent cleaning, and blow dry. So let's see what each of this option means. So first we'll see about piranha cleaning. So you have heard of the fish called piranha, which is like very ferocious when it attacks, right? So this type of cleaning is used to remove any organic residues that is present. And what we generally use is we use H2SO4 and H2O2 in the ratio of 3:1 to 6:1. So as we have higher here H2SO4 is our acid and H2O2 is oxidizing agent. So if we have a higher concentration of oxidizing agent, then the cleaning will be more vigorous. So the ratio 3:1 will be more vigorous than 6:1 because in 3:1 we have 1 parts of H2O2 with 3 parts of H2SO4. But in 6:1, we are having 1 parts of H2O2 in 6 parts of H2SO4. So this is highly vigorous piranha, and this is somewhat less vigorous. And this process is generally an exothermic process. So when we mix these two chemicals, the solution becomes very hot. And what happens is that nascent oxygen is released, which will oxidize the organic molecules, and then the organic molecules will get removed. And also in this process, some SiO2 layer is formed. So in order to remove the SiO2 layer that is formed during this cleaning, we will do an additional dilute HF dip for 1 minute in order to remove the SiO2 layer. So next is RCA cleaning. So there are two types of RCA cleaning. One is RCA1 and RCA2 cleaning. So RCA1 is used to remove organic contaminants, and RCA2 is used to remove inorganic contaminants. So both of them are done sequentially. So first we will do RCA1 cleaning, and then we will do RCA2 cleaning. In what happens is that metals are converted to hydroxides or chlorides, and then they are removed. In the case of RCA1 cleaning, we have NH4OH, ammonium hydroxide, with H2O2 and water. Then for RCA2 cleaning, we have HCl with H2O2 and water. So what we do is first we will do RCA1 cleaning. Then the same wafer we will do RCA2 cleaning. This can be then followed by HF dip if required. So both of these RCA1 and 2 can be done at higher temperature, and the ratio will depend on like how vigorous we want the cleaning to be. Then the third option that we see here is solvent cleaning. So in solvent cleaning, what we'll do is we will have acetone. We'll do cleaning using solvents like acetone, IPA. Then we will rinse it with DI water. So this can remove organic contaminants, but not as well as like it can remove some sort of contaminants, but not as well as piranha cleaning. In blow dry, we just use some nitrogen gun in order to blow any particles on the surface. So like in order to clean a new wafer after procurement, we want to remove all the organic and inorganic contaminants. So we will go with RCA cleaning. So the correct answer for problem 2 is RCA cleaning. Is this clear? Next, let's go on to problem 3. Which of the following statements is true for KOH etching? A. Before this, so KOH etching is what? It is a wet etching process, and the etch rate depends on the what type of orientation of the crystal plane that we are facing. So what are the options for this question are, the first one is the 110 planes in silicon wafer etch much slower than 100 and 111 planes when exposed to wet etchants that exhibit orientation dependence. Option B, the 111 planes in silicon wafer etch much slower than 110 and 100 planes when exposed to wet etchants that exhibit orientation dependence. In third option, we have the 100 planes in silicon wafer etch much slower than 110 and 111 planes when exposed to wet etchants that exhibit orientation dependence. So in first option, what they are telling us that 110 planes etch much slower than 100 and 111 plane. In the second option, 111 plane etch much slower than 110 and 100 planes. Then in the third option, we have 100 planes etch much slower than 110 and 111 plane. So what do you think is the correct answer? So you would have heard of like various crystallographic planes, right? So if generally we can represent the unit cell of silicon using a cube, and here the shaded portion tells which kind of plane is. So this is the 111, sorry, this is a 100 plane, this is a 110 plane, and this is 111 plane. If you look at the atoms of silicon like from this 100 plane, then we can see that the atomic density for 111 is higher compared to 110, and the least atomic density is present in 100 plane. Okay. So the activation energy that is required in order to etch away those materials will be higher for 111 compared to that of 110, and then the uh, 100 plane will have the least amount of activation energy in order to uh, etch out or break the bonds between the atoms. So like if it is having very high activation energy, then the etch rate will be very less. So if we compare the etch rate between these three crystallographic orientations, 111 will have the lowest etch rate compared to that of 110 and 111. Sorry, 110 and 100. So during the wet etching processes, we can see that the 111 plane is often used as a stopping plane, where we can it is used as a edge stop plane in order to form different types of structures by wet etching. So the correct answer for this problem is that option B. The 111 planes in silicon wafer etch much slower than 110 and 100 planes when exposed to wet etchants that exhibit orientation dependence. Okay. The reason is that the 111 planes will require like higher amount of activation energy compared to that of 110 and 100 planes, and also the atomic density of 111 plane is much higher compared to that of the 110 and 100 plane. Okay. So next we move on to problem 4. Which of the following is or are not the properties of SU8 pillars? So you would have seen that in a biomedical sensor we used SU8 pillars, right? Which of the following is are not the properties of SU8 pillars? Option A, it is a negative photoresist. Option B, it is used to make low aspect ratio structures. Option C, it is heat resistant to temperatures beyond 500 degrees centigrade. Option D, it is low etch resistance. So what do you think is the correct answer? Okay. So the answer is uh, option B and option C. Okay. Option B and option D. So first, we know that SU8 is a negative photoresist, right? So what happens in a negative photoresist? The exposed regions will get cross-linked, and they will remain, while the unexposed regions will get washed away. Then second option, what it is mentioned is that it is used to make low aspect ratio structure. So this is wrong. One thing we can see that is that in SU8, like we can have thickness from point, I think 0.2 mm. We can have this thickness of photoresist up to around 2 mm by varying the spin parameters. So we can have easily have very high aspect ratio structures. Yeah. Then option C, it is mentioned heat resistant to temperatures beyond 500 degree centigrade. So this is also false. The reason is that the SU8 has like it can be stable to temperature up to 350 degrees centigrade, beyond which like it degrades due to the high temperature. So it is heat resistant only to temperatures less than 350 degree, not beyond that. Then option D is low edge resistance. So this is false. The reason is that SU8 can have very high edge resistance, so it is used as a mask for various like for etching of various materials as well. And once it like if it hardens too much, then it is generally very difficult to remove. So it has a very high edge resistance. So like option A is correct, option B is wrong, option C is also wrong, and option D is also wrong. So here in problem 4, since we have to mention which are not the properties of SU8 plus, the answer is option B, C and D. Yeah. Is this clear? Now we'll move on to the next problem, problem 5. What is the difference between a cancer cell and a normal cell? A. Cancer cells divide irrepressibly, whereas normal cells do not divide. B. Cancer cells do not exhibit as much variability in cell size compared to normal cells. C. Cancer cells do not differentiate after division, whereas normal cells differentiate after division. D. Normal cells do not undergo angiogenesis like cancer cells. So what do you think is the correct answer? So let's say what is meant in option A is that cancer cells divide irrepressibly, whereas normal cells do not divide. Is this correct? So cancer cells divide. Uh, they divide in an uncontrolled manner, so they do not stop division. So that is correct. But normal cells also undergo division, but they have some controlled division. They do not like multiply like uncontrollably. Then so this is wrong, right? So option A is wrong. Then in option B, if we see, we can see that cancer cells do not exhibit as much variability in cell size compared to normal cells. So this is also wrong. The reason is that like cancer cells also have different cell sizes. They have various types of cell sizes. Normal cells also have like they come in various sizes. We are not the same size. So different types of cells have different sizes. So this option is also wrong. So now let us look at option D. So in option D, what it is mentioned is that normal cells do not undergo angiogenesis like cancer cells. So what is angiogenesis? Angiogenesis is the process by which uh, new capillaries are formed from pre-existing blood vessels. So this type of process plays a very important role in wound healing as well. So normal cells such as pulmonary cells exhibit angiogenesis. Cancer cells also exhibit angiogenesis. So this option is wrong, as we have like pulmonary cells which are normal cells which will undergo angiogenesis. When cancer cells undergo angiogenesis, what will happen is that they will like spread easily throughout the body. If you look at option C, here it is mentioned that cancer cells do not differentiate after division, whereas normal cells differentiate after division. So this option is correct. This is because, like, say cancer cells are multiplying into two cells, they will not after multiplying, they will not mature, so they will not like get differentiated to perform a particular function. Whereas in the case of normal cells, when they multiply, they mature, so that like they will have a particular role to play. So that is what is meant by differentiate. So they will differentiate after division, and they will perform a particular function. Whereas in the case of cancer cells, there is no like differentiation happening. Means there is no particular role assigned to the multiplied cell. So the correct answer is option C. Cancer cells do not differentiate after division, whereas normal cells differentiate after division. Is this clear? Okay. So now let us move on to next problem. Problem 6. Which of the following is a good prognostic factor in detecting breast cancer? So what is a prognostic factor? A prognostic factor is something that is used to determine whether a person is, let's say, recovering from a disease, or like whether they have uh, they have the disease is getting worse or not. So this we will use to detect it before the person goes to a later stage, like a very severe stage. So that is what is a prognostic factor. So in option A we have tumor grade 3, option B lymphatic and vascular invasion, option C tumor size, option D ER positivity. So, which of the following is a good prognostic factor in detecting breast cancer? The important thing is that the whatever factor that we are using, that should happen at a early stage of the breast cancer, not in the later stage. So, what is the answer? Okay, option A is tumor grade 3. So this happens in later stage. So this is not correct. Lymphatic and vascular invasion also happens in the later stage. So once it starts to spread, it will the cancer cells will start to spread through the lymph nodes and through the vascular blood vessels. Then tumor size is also not a prognostic factor. This is because, let's say, depending on the tumor size, we can say that the like it is in the initial stage or in the later stage. But again, we cannot. This also can be found only in the later stages, like when the tumor size becomes very high. So the correct answer is ER positivity. So what is ER? ER means it is estrogen receptor. So if we are having like breast cancer cells which are testing positive for estrogenic receptors, then it is called as ER positive breast cancer. So by uh, having test for this kind of receptor, which is also a biomarker, we can detect the presence of breast cancer. So, like there are other receptors as well. One is HER and the other is PR. Okay. So, if PR and ER. So, if any of these biomarkers are found positive, then we can say that like the breast cancer is due to that particular receptor. Next, we'll move on to problem 7. What is the material that is used for a micro heater? Option A, chrome gold. Option B, silver. Option C, tungsten. Option D, nichrome. So what is a micro heater? So a micro heater is a MEMS device that is used to generate heat, and it uses the Joule's effect. So So what is Joule's effect? When like heat is passed through a conductor, which means a wire that is having some finite amount of conductance. Sorry. So the microheater works based on the Joule's heating effect. What is the principle of a Joule's heating effect? In Joule's heating effect, the heat is generated from a conductive material when there is some amount of electric current that is flowing through the conductor. So, like since we know that like we are having a wire which is having some sort amount of finite conductance, and we are passing current through the wire and heating it. So, which material do you think is best for a microheater? Okay, so since we are heating this kind of material, let us look at the melt resistivity of these kind of materials. Okay. So if you are having chrome gold, the resistivity is around 2.44 into 10 power minus 8 ohm meter. For silver, the resistivity is 1.59 into 10 power minus 8 ohm meter. Tungsten, it is 5.6 into 10 power minus 8 ohm meter, and for nichrome it is 150 into 10 power minus 8. So here you can see the resistivity of various materials. So if we see like uh, since we want to pass current through a wire, the resistance of the wire will determine how much amount of heat is generated. So we need a material which is having the highest resistivity. Here you can see that nichrome is having the highest resistivity among all the materials. So nichrome is a very good choice for a micro heater. Another important thing to note down is that uh, in addition to it having very high resistivity, it also has a very high melting point compared to other metals. So, and also it does not get oxidized easily even though it is at higher temperature. Okay. So before we move on to next question, I would like to tell something about the Joule's heating effect. So we know that resistance of a wire is R as rho, which is the resistivity into length divided by A. A is the area of the cross section of the conductor. L is the length of the wire, and rho is the resistivity. So here we can see that if we are having a higher resistivity, we can have a higher resistance, and also by having a large a wire with large length, we can have high resistance. So if you see Joule's heating effect, the amount of heat that is generated by the Joule's heating effect is given by I squared R into T, where T is the time and I is the current flowing through the wire, R is the resistance of the wire. So generally we need a material with very high resistivity and also with a very large length. So if you look at micro heaters, some of the like figures of micro heaters, you would see that like they will have this kind of structure, something like this. So why they are arranged in this kind of folded fashion is that in MEMS, generally we want to fabricate devices which are very small and like occupying less area. So in our heater, if we want large amount of heat generated, we need a larger length. So if we need a larger length, if instead of just making the wire straight, uh, mean if we are making the wire straight, then we'll need a very large area. But instead of that, if we fold the wire like this, then we can occupy more length. We can have more length of the heater in a small area. So that is one of the reasons why we have like the heaters in this kind of folded configuration. Okay. So is this clear? So the answer to problem 7, what is the material used for micro heater is nichrome, and the main reason is that It has very high resistivity and high melting point. Also, it is not easily oxidized. So nichrome is a alloy of nickel and chromium. So now we'll move on to the next question. Problem 8. What are the three modalities of tissues that can be studied using a MEMS biochip to diagnose breast cancer? So here, like by modalities, what we are meaning is like what type of properties of tissues we can study to diagnose breast cancer. And the device that we are using is a MEMS biochip. Okay. So what do you think are the three modalities or three properties of a tissue that we can study? Hmm. Okay. So the answer is in addition to biomarkers, we can use the following three properties to diagnose breast cancer. One is electrical, the second one is mechanical and thermal. So in electrical, what we can do is we can place the cancerous tissue between two electrodes, apply some voltage, and when current flows through the tissue, we'll have some different, we can measure some different electrical property, like which is the impedance will be different. So by measuring the change in the impedance between a breast cancer tissue as well as a healthy tissue, we can find out whether a person is having a disease or not. Then in mechanical, we can measure the stiffness of the tissue. So in electrical, we'll be measuring the impedance. So by measuring the stiffness of the breast tissue, we can determine whether it is a cancerous tissue or a healthy tissue. In thermal, what we measure is the thermal conductivity. So we use microheaters to heat the cancerous tissue, and we will determine the thermal conductivity. So these are three important parameters that can be used in addition to biomarkers to diagnose the breast cancer. One important advantage of like using this kind of properties to diagnose is that like if certain people are having uh, like negative when they are testing for the biomarkers, if they are having negative but they are actually having cancer, then like by instead of measuring the biomarker concentration, if they measure the properties of the cancerous tissue, then they can diagnose the disease. So now let's move on to next problem. Problem number 9. Carcinoma is a cancer involving which tissue? A is embryonic, B epithelial, C connective, D is bone. So which tissue do you think is causing cancer? So what is carcinoma? So what is a carcinoma? Okay. Carcinoma is a type of cancer that is affecting the epithelial tissues. So the answer is option B. So uh, if we are having a cancer of embryonic tissue, so embryonic tissue is fetal tissue. If you are having cancer in fetal tissue, then they are called as either as neuroblastomas or Wilms tumor. And in some cases, they also call this type of cancer as embryoma. So carcinoma is a cancer that is affecting the epithelial tissue. So like we have a epithelial lining in most of the organs. So if there is cancer in that epithelial tissue, then it is called as carcinoma. And if we are having bone cancer, then what we call it as there are many different types of bone cancers. So one of them is osteosarcoma. If there is any cancer in the connective tissue, then it is called as sarcoma. So connective tissue means it will cancer will occur in fat, muscle, nerves, or tendons, or even in cartilage. So epithelial tissue means it is a tissue that is lining all the organisms, all the organs, vital organs. Okay, so bone is generally called as osteosarcoma. The correct answer to problem 9 is carcinoma is a cancer involving epithelial tissue. Okay, so that is the correct answer. Next, we'll move on to problem 10. Can the cancer diagnostic tool MEMS biochip discussed in class detect triple negative breast cancer? So what is the MEMS biochip? The MEMS biochip that was discussed in the lecture, right? That is a lab-on-chip device which was having heater, interdigitated electrodes, and so on. So, what is a triple negative breast cancer? We know that there are like certain receptors which are called as biomarkers that can be used to detect whether a person is having cancer or not. So some of them are one is ER receptor or PR receptor or HER receptor. So ER receptor is called estrogen receptor. PR receptor is called progesterone receptor. And HER, there is a receptor, so that is some type of protein based receptor. So triple negative means the whatever test that we are having for cancer is showing negative for all these three types of receptors. So in that case, what happens is that it becomes a false diagnosis. Means a person is having cancer, but from the test, it is telling us that none of these three receptors are causing cancer, right? So if we are having a MEMS based biochip, where we measure the mechanical, electrical, and the thermal property of a tissue, we can easily identify whether a person is having cancer or not without the need to look at the biomarkers. So even though like the test regarding the biomarkers comes as negative, by just measuring the thermal, electrical, and the um, mechanical properties of the tissue, we can diagnose the cancer. So the correct answer is true. Option E. Okay. Next is problem 11. What transduction scheme is used in the MEMS biochip to detect the mechanical property of a tissue? So this, I think we saw in one of the previous questions, that we can measure the mechanical property of the tissue. And what type of mechanical property are we measuring? We are measuring the stiffness. So by there will be a significant difference in the stiffness between a cancerous tissue as well as a healthy tissue. So by determining what like the stiffness we can measure. So what kind of sensing scheme is used to measure the mechanical property? And also one important thing is, in all the sensors that we use, we need the output in some form of electrical signal. That is what we can read out, right? So we need some sort of transduction scheme that can convert mechanical into electrical. And in our case, we are converting some stiffness into electrical. So what kind of scheme can we use? The answer is piezoresistive. So in piezoresistive scheme, what happens is that any change in the strain in the material will get converted to change in resistance. By connecting this piezoresistor in a Wheatstone bridge configuration, we can get a voltage output for the change in the strain in the circuit. And what we have is that we'll have some SU8 pillars that will act as some sort of indenter, or we'll just have some indenter. And this indenter will be used to transfer some amount of force to the tissue. Depending on the elasticity of the tissue, the indenter will like give some amount of force to the uh, give back to the sensor. And if the particular sensor is having some piezo resistor, then we can easily measure the stiffness of the tissue. So how do we measure the stiffness of the tissue? First is that we know that the sensor or the chip is having some sort of piezo-resistive material. So if we are having an indenter and if we are pressing the tissue, then the tissue will have some sort of force that is given. But due to the elasticity of the tissue, the amount of force that is transmitted from the indenter to back to the sensor will depend on the how much the elasticity is present in the tissue. What kind of transduction scheme are we using? We are using a piezoresistive transduction scheme. What we will do is we'll use the indenter to apply some force on the tissue. Depending on the elasticity of the uh, tissue, it will like give some amount of like feedback force. So with that force, we can deform. Let's say if we are having some sort of micro pillars on a diaphragm like structure. Okay. And we are having some piezo resistor at the regions where there is high amount of strain. So if we use this micropillar in order to indent the cancerous tissue, then what happens is that depending on the stiffness of the tissue, this will experience some sort of force. So this force is then transformed to this diaphragm. Then this diaphragm will experience some sort of strain because there is some sort of deformation that is happening. When we keep the piezo resistor in the regions of high strain, like in piezo resistor means what? There is some change in the resistance of the material under the application of some sort of force. So like we'll have some change in the resistance due to change in the strain. By connecting these types of piezo resistors in some sort of Wheatstone bridge configuration, we can measure how much change in the stiffness of the tissue is present when we are using different types of tissue, like some sort of healthy tissues and some unhealthy tissues. So the answer is piezoresistive transduction scheme. Next, we'll move on to problem 12. Why can't we use wet or dry oxidation in LPCVD to grow a SiO2 insulating layer on metal structure? So what is LPCVD? LPCVD is low pressure CVD, chemical vapor deposition. So what happens in LPCVD is that we are operating the system at very low pressure. So generally, in order to control the deposition process, we'll have very high temperature. And we know that like very high temperature means we will have greater than 800 degrees centigrade. So most of the metals have lower melting point than 800 degree. So they will not be able to survive those high temperatures. Right? So that's why We cannot use any wet oxidation or dry oxidation in LPCVD in order to grow SiO2 layers. And what we will do instead is that we will use some low temperature deposition process such as PCVD, which is plasma enhanced chemical vapor deposition technique. So in this technique, what we'll do is we'll supply the energy that is required for the chemical vapor deposition by using plasma. So since most of the energy that is required for the reaction to happen is supplied using plasma, we can do the process at a lower temperature, like in 200 degree or 200 degree to 350 degree centigrade. Okay. So the answer to problem 12, why can't we use wet or dry oxidation in LPCVD to grow SiO2 insulating layer on metal structure is that the high temperature will melt the metal. So we are using PCVD instead, which is a low temperature process. Next, let us move on to problem 13. Okay. What is a desiccator used for? Option A, heating substrates. Option B, cleaning the substrate. Option C, disposing waste. Option D, storing substrates in vacuum. So first, before that, do you know what is a desiccator or have you seen any desiccators? Okay. So here you can see that like this is an image of a desiccator. So these two are desiccators. So these are generally sealed containers that are used to dry the samples in some vacuum condition. So what we'll do is we will pump the desiccator into vacuum and then we will seal it in vacuum process. So these are generally used to protect the samples from dust and moisture from the air. So the desiccator is generally used for storing the substrates in vacuum condition. So this is one of the common ways by which we store the samples that are being processed during the fabrication processes. Is this clear? Next, we'll move on to the next question. Problem 18. SU8 is a negative photoresist. Areas of wafer covered with SU8 when exposed to UV light, what will happen to the exposed area? Option A is hardened, B is softened, C remains the same, D cannot be determined. So SU8, what do you think the answer is? It's a negative photoresist, it's mentioned, right? And it is optically sensitive. It is optically sensitive to the UV light. So what happens with the negative photoresist? Negative photoresist are like certain types of photoresist where like the regions that are exposed to the light will harden and they will get remain. So what happens is those regions will undergo some process called as cross-linking. So they will not be they will not get dissolved in any organic solvent, whereas the regions which are unexposed will easily get dissolved in the solvents. So what is a negative photoresist? A negative photoresist is one in which which has whichever region the light is exposed will harden or cross-link, whereas the regions where the light is not exposed will get dissolved in the developer. Okay, so if you are having a mask like this and this is a region which is opaque, so which is having chrome and you are having your SU8 coated substrate. So since SU8 is a negative polymer, what will happen is in the regions where the light will get exposed, the SU8 will harden and it will remain So this is due to the cross-linking process. So after developing, this is how it will look. And the regions where which did not have any light exposure will easily get dissolved in the solvent. So the answer is the exposed area will harden. The correct answer is option E. Is this clear? What happens if it is a positive photoresist? If it is a positive photoresist, then the exposed region will soften, meaning it will easily get dissolved in the developer. If this is clear, then we can move on to the next problem. Problem 15. So in problem 15, we have to select the correct combination. We have some different combinations of input energy, output energy, as well as material property. Right. So in option A, we have electrical input, mechanical output, and the material property is said to be electrostrictive. In option B, we have magnetic input, thermal output, and the material property is called as magnetoresistance. In option C, we have thermal input, electrical output, and the material property is called as pyroelectric. In option D, we have mechanical input, magnetic output, and the material property is called as magnetostriction. So first, what is electrostriction? Electrostriction is a process by which when we are applying some sort of electric field to a material, it will cause some sort of deformation, mechanical deformation of the material. So option A is the correct answer, where we are giving electrical input and giving some mechanical output. So electrical input and we are getting some mechanical output. Then now if we look at option B, the input energy is magnetic and the output energy is thermal. So in magnetoresistance, what actually happens is that when we are applying some sort of magnetic field to a material, there will be some change in the resistance of the material. So that type of property is called as magnetoresistance. But here our input energy is given as magnetic. Okay, that is correct. But output energy is thermal, so that is wrong. The output energy is resistance, change in resistance, which we can say as electrical property. So this is wrong. If we look at option C, okay, so now let us look at option C. So in option C, what we have is we have an input energy which is thermal and output energy which is electrical, and the material property is pyroelectric. So pyro means heat. So in pyroelectric materials, what happens is that when we are changing the temperature of the material, there will be some voltage that is developed across it due to the change in the polarization of the material. So that type of materials are called as pyroelectric materials. So here, since the input energy is thermal and the output is electric, this is correct. Then if we look at option D, where we are having input energy mechanical, output energy magnetic for the material property magnetostriction. So magnetostrict materials are materials which exhibit some sort of mechanical deformation under the application of magnetic field. So like for a magnetostrictive material, the input should be magnetic and the output should be mechanical. Since it is given in opposite, this is wrong. So the correct combinations are option A, input energy electrical, output energy is mechanical, and the material property is called as electrostrictive. Option C, where the input energy is thermal, output energy is electrical, and the material property is called as pyroelectric. These are the correct answers. Okay. Next, let's move on to problem number 16. Match the following. So in left we have some options, and in right also we have some definitions for various terms in the left side. So you just have to match which is the correct one. So photolithography, microfluidics, piezoelectric material, silicon, lab on chip, etching, biomarker detection. So these are the options on the left side. So what is the answer? So what is photolithography? Photolithography is a technique by which we are using we are transferring some sort of pattern onto substrate by using light and mass. So photo means light, litho means to write. So this is option E, the technique that is used to transfer a pattern onto a substrate by using light and mass. Okay. Then what is microfluidics? In microfluidics, what we will do is we will study and manipulate tiny amounts of fluids within small channels. So that is option F. One is E, two is F. What is a piezoelectric material? A piezoelectric material is something that will generate some voltage when mechanical stress is applied. So that is option B. Is B. So these kind of piezoelectric materials are generally non-centrosymmetric. They should have this non-centrosymmetric property. Then only when we are applying some sort of mechanical force to the material, we'll be getting some sort of voltage. Otherwise, we will not have this kind of effect. So what is silicon? So silicon is what? It is a central component of MEMS fabrication used in the substrate. So 4 is option C. Next, a lab on chip is something that is a miniaturized device which is integrating multiple laboratory functions on a single chip. So 5 is options D. 5 is option D. Then etching is the process by which we are removing material in order to create patterns and structures on a substrate. So option 6 is A. Biomarker detection is something where we are identifying specific molecules which will indicate that whether a disease is present or not. So 7 is option G. So these are the correct answers. Is this clear? Now let us move on to the next problem. Problem 17. Which of the following statements are incorrect? A. DRIE provides a large aspect ratio etching capability. DRIE etches with different rate depending on the directions or the multiple directions, which is depending on the orientation of the silicon. Then option C is DRIE enables faster etch rates and the formation of deep etch structures. Option D is DRIE uses chemicals to etch out surfaces. Option E is the sidewall of etch profile results in scalloping due to repeated polymer deposition and etching for sidewall protection. So what is the answer? So first option is correct because we know that DRIE, the name as the name suggests, it is deep reactive ion etching. So we are making very deep trenches. So it is having a very large aspect ratio etching capability. This is correct. Then DRI etches with different rate depending on multiple directions. The directions which are depending on the orientation of silicon. Is this correct? It's wrong. So this kind of orientation dependent etching will happen only in the case of wet etching processes, not in dry etching. Because the reactants that are used in dry etching do not have any orientation dependent sensitivity. So generally we use SF6 for etching silicon. So that is an isotropic etchant. So it will etch equally in all the directions. It does not depend at what orientation the silicon is. Okay, so this is one of the incorrect statement. Then DRIE enables faster etch rates and the formation of deep etch structures. So that is correct. Then DRIE uses chemicals to etch out surfaces. So this is also correct. Then E is the sidewall of the edge profile results in scalloping due to repeated polymer deposition and etching for sidewall protection. So how do we like get these deep as or high aspect ratio structures? That is because we are doing repeated polymer deposition and etching. So because of that, we will have something called scallop. So this is also correct. So the only statement that is incorrect is option B. So here, the answer for problem 17 is option B, where we are telling DRI etches with different rate depending on multiple directions, depending on the orientation of silicon. So this is totally wrong for a dry etching process. So if we look at the various not various cycles, various steps in one cycle of a DRI process, we will have polymer deposition where we use a polymer C4F8. So this will deposit some sort of passivation film which will protect the sidewalls. Then we will be passing SF6 gas along with plasma. So this will do etching. So generally this SF6 is isotropic etching, so it will etch equally in all the directions. Since the sidewalls are protected, they will like the polymer that is present at the this at the bottom will get etched faster, whereas at the sidewalls it will still remain somewhat. So in the subsequent steps, once the SF6 etching is done, what we will have is we will have some isotropic profile in the regions where there is no polymer protection. So in the next step, again polymer will get protected everywhere. So we will have like more protection in the sidewalls in the top. So as the so initially, let's say if we are having a mask like this. In the first step, we'll have some protection with SF6. So it will protect everywhere. Sorry, protection with C4F8. So it will protect everywhere. Then once SF6 gas is passed, it will start etching isotropically. What happens is that it will create this kind of profile when it etches below the mask. In the next cycle, we will after the etching, we will again do polymer deposition. So polymer will get deposited everywhere, and it will also get deposited in the sidewalls as well as at the bottom. When the SF6 etching happens, it will so this protected polymer will remain as such. However, here it would have etched again isotropically. So we'll have formation of something like this. The side walls after etching will appear like this. So these are called as scallops. So this is one characteristic feature of the Boss DRI process. Is due to like the cycle which is having polymer deposition step and etching step. So is this clear? In problem 17, the incorrect statement is option B, where DRI etches with different rate depending on multiple directions, depending on the orientation of silicon. So that is a wrong statement among the options that is given. So any other questions? If not, we can end this session. Okay, thank you.